Hey everybody, we're going to finish off chapter 6 today. We're going to continue our study of rational functions, which we began back in the core book. And we're going to see a technique known as partial fraction decomposition, which is a way to rewrite rational functions from one form into another. You'll see what I mean in just a few minutes. This is a technique that was not required in the previous version of Mathematics HL. So if you're looking at any past papers or talking to a friend or sibling who took the course in the last 7 years looking for help, they may not know it or they may not know its name. But it's helpful. I've included it in my classes because I think it's a nice technique to use, and it's going to be very crucial for us to know in particular once we get up to calculus, specifically integral calculus. But that's a conversation for another day. For today, we'll just stick with some algebra. All right, so back in the core book, we saw rational functions that looked like that, a linear divided by a linear. And now we're just going to talk about a linear divided by a quadratic or a quadratic divided by a linear. No problem. We can really think about them in the same way. There's honestly not a lot of new stuff to consider here. If we have a quadratic in the denominator, the horizontal asymptote is going to be y equals 0. Why is that? Because we can think about what happens when x gets super, super, super big in either the positive or the negative direction. We are going to have a denominator which is much, much, much larger than the numerator because we have an x squared term here and only an x to the power of 1 there. Therefore, the denominator, because it's so much larger than the numerator, we're dividing a small number by a big number, it's basically going to be equal to 0. And that's going to be true really regardless of what the exponents are. And this is going to be an important thing for us to consider when we get to calculus. If we've got a denominator with a higher degree than the numerator, then the horizontal asymptote is always going to be 0. And the vertical asymptotes, that's the same as what we considered before. It's just going to be when the denominator is equal to 0. So we have a quadratic in the denominator. We can set it equal to 0 and go from there. So looking at an example really quickly, here we've got a function. First thing we want to do, find the asymptotes. Horizontal asymptote obviously is going to be 0 because I have a linear divided by a quadratic. Awesome. Vertical asymptotes, that's a quadratic. That looks like it's going to be easily factorable. So I'm just going to do that to find the zeros. There we go. Then we have the vertical asymptotes now. Letter B, find the axes intercepts. For the y-intercept, we're just going to set x equal to 0. That's very easy. We look at this. It's going to be -6 divided by -4. Awesome. For the x-intercept, we're going to set y equal to 0, which means we're really just interested in the numerator. Set the numerator equal to 0, and we get the x-intercept. Nothing special here. This is exactly what we would have considered when it was a linear divided by a linear, right? And everything here extends to beyond linear and quadratics. This is just, the techniques are general no matter what type of rational function we have. Okay, now that we know the x-intercepts and the zeros, we can draw a sign diagram, horizontal line, list those numbers, and then we choose test points in between them and figure out whether it's positive or negative. Hence, we can discuss the behavior of the function near the asymptotes. So in other words, near the horizontal asymptotes, is it approaching the horizontal asymptote from above or below? Well, I see right here, as we go out to -infinity, it's approaching from below. And as we go to positive infinity, it's approaching 0 from above. And as we get closer to the vertical asymptotes, I should say, -1, as it approaches that from the left, it's going to -infinity. As it approaches from the right, it's going to positive infinity. Same situation over here for 4. So that's communicated here. And then finally, using all the information that we've just discussed, we can draw a good sketch for this function. And there it is. And that's not a trivial thing. That's a fairly complicated looking function. But if we just follow a few simple steps, we can get a pretty decent looking picture of it. Now, of course, on the IB exam, you're not likely to be walked through, with your hand held like this. You're not going to be reminded, oh, hey, make sure to draw a sign diagram, make sure to check for the x and y intercepts, etc. You need to remember to do all this stuff. But you should be able to come up with something like this. And as we said before, once we know some calculus, we'll be able to identify other special points, like there's something right around there where the concavity is changing, but you don't need to know anything about that just yet. Now, obviously, not every rational function in the form of a linear divided by a quadratic will look exactly like the one that we saw. Depending upon what those coefficients are, we could get lots of different looking things, but the process of analyzing them will be exactly the same. When our quadratic function is in the numerator, or more generally, when the numerator has a higher degree than the denominator, we're going to use polynomial division, which we saw last chapter, to rewrite this function in this form. Now we can find the vertical asymptotes by focusing there. Whenever that denominator is equal to 0, we will have a vertical asymptote. There's not going to be any horizontal asymptotes because of the fact that the numerator has a higher degree than the denominator, but we will have something called an oblique asymptote. This is another topic that was not in the previous curriculum. Previously, we would have just said, oh, as x gets larger, y gets larger. It just goes off to infinity or down to negative infinity, whatever. But now we're going to actually have to analyze how exactly is it approaching infinity. So these oblique asymptotes are essentially, the function is essentially becoming like a particular line heading off to infinity or negative infinity. And that particular line is just this part here, because as x gets larger and larger and larger and larger and larger, either in the positive or negative direction, that r over dx plus e term drops down to 0. So what we're left over with is the px plus q. And that's going to be our oblique asymptote. Now this is particular to the fact that we have a quadratic divided by a linear. If we had different degree functions happening up there, then we might not get a slant asymptote out, but we will in this case, and this is the case that the IB cares about. So you can worry about those other situations when you go off to university. Okay, so let's get a sketch of this thing going. So vertical asymptote and axis intercepts. Here they are. Vertical asymptote, obviously x equals -2. We see that from the denominator. Axis intercepts, y-intercept, we set x equal to 0. Easily done, -9/2. For the x-intercepts, we're going to set y equal to 0, which again just means we're setting the numerator equal to 0. So we find the zeros of that quadratic. We got them. Next, oblique asymptote. So we're going to have to rewrite this using polynomial long division. Everybody loves that, right? So we can rewrite our original function as 2x minus 1 minus 7, that's our remainder, divided by x plus 2, which was the original divisor. And then this part right here, the 2x minus 1, that is our slant asymptote. Next, we're getting a sign diagram so that we can discuss the behavior near the asymptotes. So our sign diagram, again, we get the zeros and the vertical asymptote here. Choosing test points, awesome. We'll start with the vertical asymptote, -2. As x approaches -2 from the left, f of x is headed up towards positive infinity. As x approaches -2 from the right, f of x approaches negative infinity. Now for the oblique asymptotes. As x approaches negative infinity, what we used to write would have been f of x approaches negative infinity, because the sign diagram says f of x is going down. And likewise, we used to say as x approaches positive infinity, f of x is approaching positive infinity. But now, we're not going to say that. Instead, we're going to say that f of x is, in both of these cases, approaching the line 2x minus 1. And then we just need to state whether it's approaching that line from above or below. And I don't know, maybe there's a better way to do this, but my brain is stuck thinking in terms of calculus, and we're not allowed to talk about that just yet. So here's how I would figure out whether it's above or below. And again, I need you to pretend that you can't see this picture over here, because obviously if you could see the graph, then it's kind of easy. But we know that the y-intercept, so when x is 0, the y-intercept is -9/2. So I'm just throwing that into my sign diagram. And I know that the line 2x minus 1 has a y-intercept of -1. Now, -1 is above -9/2. So that means that as I'm moving out here to the right, my function is starting off below the line 2x minus 1. So it needs to be approaching it from below. And then likewise, if we think about going out towards negative infinity, we know that my function is starting off up here at positive infinity, and then is kind of generally getting lower and lower and lower. So it must be above the line 2x minus 1. So we say here that it approaches from above. Okay, so onward to partial fraction decomposition. To decompose a rational function, this means we're going to rewrite it as a sum or difference of two or more fractions. They're called partial fractions because they each make up part of the original whole. The steps we're going to follow are on screen. I have nothing else to say about them, so jot them down if you need to. So I'd like to start off with something kind of easier. This is an example from the core book that I think was in a previous video. So the original function is 2x plus 1 over x minus 1. And to remind you, because the book's technique isn't really expressed in words, basically they're looking at the denominator, which is x minus 1, and they're going to say, okay, we're going to change this x into an x minus 1. So we're rewriting 2 times x minus 1. And now, well, we need the rest of the numerator to still be the same. So currently it's going to be 2x minus 2, but I need it to be 2x plus 1. So we're going to add in this extra plus 3. And now we have a fraction which has a sum or difference in the numerator, right? So we can split the fraction right there. We get 2 times x minus 1 over x minus 1, but those x minus 1s will cancel, leaving us with just 2, plus 3 over x minus 1. And that's a partial fraction decomposition. In this case, the two fractions were just 2 over 1 and 3 over x minus 1. They just didn't use the method of partial fractions. Here's what that would have looked like. We take our original function. The denominator is already factored. That's great. So I'm going to write a sum of two fractions, one of which has the same denominator as before, and the other one's going to have a denominator of 1. 1 times x minus 1 is equal to x minus 1. We just don't know what the numerators for those two fractions are, so I like to call them a and b. And the claim is that our original function is going to be equal to this sum for all values of x. We just need to figure out what a and b are. Now, I'm not offering a proof for you that this actually can be rewritten in this form. It's not immediately obvious that it must be able to be broken down, especially when we get into more complicated fractions. But as with many things, we're just going to go with it. You get to learn real math when you go off to college. Next step is we're going to multiply everything through by our original denominator. So now what we're going to do is we're going to figure out what a is, because remember we said that these are going to be equal no matter what the value of x is. So we're going to conveniently choose a value for x that gets rid of this entire term. We're going to choose the value of x where the original 0 of the denominator, to follow our steps from the previous page. That 0 is x equals 1. So if we assume that x equals 1, and we can see pretty quickly that a has to be equal to 3. We can then substitute that in here and then just compare these two sides to quickly work out what b is. Comparing coefficients, b has to be equal to 2 to get the linear coefficients equal, and then conveniently 3 minus 2 gets us that 1. So we can rewrite our original decomposition up here with a as 3 and b as 2. And you'll notice that matches exactly what we got there. Now, perhaps that seemed like a lot of work for this question. That's fine. Maybe the book's technique is more efficient for a simple one. However, we're now going to see some more complicated ones where this technique will be very helpful. So, more complicated looking function here. Step 1, we're going to try to factor the denominator. Okay, we've got x minus 2 and x plus 3. So our answer should be in the form of some number over x minus 2 plus some number over x plus 3. We're now going to multiply through by that original denominator. And what we're going to get is we're going to notice that the x minus 2 factor will cancel here and the x plus 3 factor will cancel there. And now we're going to play the exact same game. We're going to set up two cases. We're going to substitute in x equals negative 3, and we'll substitute in x equals 2. When we put in negative 3 and then 2, it cancels out one of the terms, so we don't even need to worry about it. We quickly find out what b and what a are, and that gives us our partial fraction decomposition for this function. And we could do this the same way even if there were, say, 3 or 4 different linear factors of the denominator. However many there are, we can just approach it in the exact same way. We would just have a over something plus b over something plus c over something, etc. And those factors do not need to be in the form of 1x plus whatever. They can be, ax plus b, any general linear factors, as long as none of those factors are repeated. Once we have some sort of multiplicity involved, the process becomes just a little bit more complicated. I grabbed this chart from a wonderful website called Paul's Online Notes, just to give you kind of an idea of what's happening here. So when we look at our original rational function, when we see that there is a factor in the denominator that's linear, which is what we just looked at, that's going to correspond to a term in the partial fraction decomposition, which is some constant divided by that particular linear factor. So that's exactly what we saw in the previous one. There happened to be 2 linear factors, which corresponded then to 2 terms in the partial fraction decomposition. But here, we have a linear factor that is repeated some amount of times. And the way that that's going to work in our partial fraction decomposition then is that we're going to have, just for this single, well, I shouldn't say single term, but for this particular repeated factor, that's going to correspond to some constant divided by that factor to the first, plus some second constant divided by that factor to the second, all the way up to some constant divided by that factor to the power of k. So if this were ax plus b to the power of 7, then we would have had 7 terms there. For the IB, we're going to, 2 is going to be our maximum, so we don't need to worry too much about it. And also for the IB, we don't cover unfactorable quadratics, but we've got rules for it here. If you had a quadratic in the denominator that you couldn't factor, that would correspond in a partial fraction decomposition to a linear numerator divided by a quadratic. And similarly, to generalize that below, if we have a repeated quadratic, that'll correspond to a series of linear divided by quadratic terms. Again, I offer you this without proof, but I think it is worth noting before we move on that the first and actually the third cases are just special cases of the second and fourth ones. When we have x plus b just to the power of 1, that would correspond over to the right to being just that first term, which is exactly what we see up there. So the general rule is worth considering, I think. So here's an example of that. Now, the question in this case told us to rewrite it in this particular form, where we have a single term divided by x plus 1, because that factor only appears once, plus some constant divided by x minus 2, plus another constant divided by x minus 2 squared, because we have that repeated term. But we didn't need to see any of that. We could have worked that out just from noting that we have one distinct factor, x plus 1, and one repeated factor, x minus 2. So we're going to approach this the same way as we did before. We're going to start off by writing it in that form, and then we're going to multiply through by the denominator, the original denominator. Stuff's going to cancel, and we've got ourselves here. And now we're going to choose zeros from the original denominator to eliminate certain values in a convenient manner. So when we put in x equals -1, we see 2 terms are going to drop out, right? And that tells us that a is equal to 5. And then when we choose x equal to 2, these 2 terms will drop out. That'll get us our c value. And now we need to figure out what b is. It's just like before, we have 2 different ways we could proceed here. The easier option, I think, is just to substitute in any other value for x into the expression, and then you can figure out, since you know what a and c have to be, you can figure out what b is. Or you could combine a whole bunch of like terms on the right-hand side and then compare coefficients, whatever makes you happy. One example that I didn't see in the book is something like this. So you may have noticed in the previous ones that the degree of the denominator was always higher than the degree of the numerator. And that's great when it is. But if it's not, then you can't proceed with partial fractions right away. You have to do just a little bit of work first. And that little bit of work is our old friend, polynomial long division, which I'm not going to show, but it will get you there. And then we can factor the denominator x squared minus 4, and we can perform partial fractions, which in this case gets us some not particularly friendly values for a and b, but whatever. And then you're good to go. You can rewrite those. Of course, it's like 9 over 4x minus 8, and etc. But we'll do whatever the problem calls for, I suppose. Anyway, that's it for partial fractions. I won't do any examples with an unreducible quadratic denominator because, as far as I can tell, the IB is not interested in that. But you can certainly look it up on your own. And again, that's all for this topic for now, but it will come back again when we get up to calculus. There won't be any new information or techniques regarding partial fractions, but we will be expected to remember it in order to handle some nasty integrals. But we can worry about that later.